In this first video, let's look at the one of the base assumptions which we make regularly, and that is related to sample size. Why n greater than equal to 30 is considered statistically sorry, I missed one I here significant. Now the answer to this lies in what we call central limit theorem. To understand this better, let's start with illustration. Let's start with a universe of n equal to 10,000 car owners of brand X. And let's say we measure satisfaction of these owners on a 5-point scale, and the distribution of this satisfaction is skewed towards positive, which is usually the case. Now technically, if I have to measure the satisfaction of these 10,000 car owners, we can look at any number of sample size. Now in reality we look at various levels depending upon various issues. Now let's say theoretically we can look at one. We can look at a sample size of 1 and say let me take any random person and understand the sample. And what we'll get is something like, say, a satisfaction of 4. I can look at n equal to 2. In that case I'll get something like 4 and maybe 1 5, and we can look at n equal to 3 where we'll get something like 4 and a 5 and maybe a 1. Similarly, we can keep on looking at various combinations, and the maximum of that would be 10,000 because that's the finite universe, and would look like something like 4 5 1. I'm not going to write all the 10,000 numbers, but say assume the 10,000 number is 2. Now central limit theorem, what does it say? Now central limit theorem says 3 things. 1, irrespective of the sample size, which we take 1, 2 or 3 or 500 or 10,000, if we repeat it sufficiently large number of times, and then the means of the mean which we get here. That means if I take 4 and then maybe I repeat it another time, I get 5, another time 1, another time 3, and then 2, and what we get something around what we call, let's call it as x1 bar. Similarly in this case it's 4 and 5 is a combination. Now an average of this is 4.5. Similarly there would be a combination of say 1 and 3, so it's 2, and similarly in other combinations, and we call it average of x2. And similarly we'll have various combinations. If we take 3 sample size, then in my first picking I get 4 5 1. If I pick it again I will get something like, can be anything between 3 1 5. So if we take an average of this, it would be 3.3, and this would be 5 plus 3 8 plus 1 9, so it will be 9 divided by 3 is 3. So we get something like that, and let's call it x3 bar, and similarly here it comes to x 10,000 bar. Now what first rule of central limit theorem say that irrespective of the number of sample size, your mu, or mu is essentially the mean of this 10,000 universe. Mu, which is the mean of the universe, is equal to x1 bar, is equal to x2 bar, is equal to x3 bar, and so on. Second thing it says is that irrespective of the distribution type, whether it's positively skewed, negatively skewed, the probability distribution of these means will always follow a normal distribution. If we repeat it sufficiently large number of times. Now those who don't know normal distribution, it looks something like this. Like this, with a higher peak in the bottom and lower probability towards the tails. And in this normal distribution, if you see, the midpoint is the mu, which is equal to x1 bar, is equal to x2 bar, and so on. Now the third point here is, while the mean will always be equal for any sample size, what will differ is the variance. So what will differ is how much is the variance between the points here. And the variance is calculated by looking at sigma x is sigma by root n. So that means higher the n, lower the sigma x. So the variance will be the lower as the sample size is increased. Now what does all these mean? Now basically what all these mean is that if you go back to the normal distribution, if the sample size increases, if you see it increases from 1 to 2 to 3 to n, the moment it's crossed something like n equal to 30, what we get here is standardized normal distribution. Now what is standardized normal distribution? Now standardized normal distribution is a normal distribution where the difference between the variance and the area under different variance levels is clearly known and which is standard. In this case, if you see here, the first line is the difference is 1 sigma, the second line is 2 sigma, third line is 3 sigma. Similarly here, 1 sigma, 2 sigma, 3 sigma. Now this 3 sigma and 3 sigma adds up to 6 sigma, and if you are wondering, yes, this is from the place where 6 sigma comes from. Now in a standardized normal distribution, the area from the mean to 1 sigma is 34.1%. Similarly here 34.1%. Between 1 sigma to 2 sigma is 13.6%. This is 13.6%. And from 2 sigma to 3 sigma is 2.1% and 2.1%. Now this area within the normal distribution is fixed, and that's why it's called standardized normal distribution. Now the advantage of having the standardized normal distribution is we can calculate something which is called Z statistic. Now I'll come to the Z statistic and the implications in the future video. Once we are able to calculate the Z statistic, we can do significance testing. And hence, when n is equal to greater than 30, we can do significance testing. And significance testing becomes valid. We can technically do at any sample, but it becomes valid because if n is greater than 30, the distribution, normal distribution, is standardized, and therefore the Z statistic is valid. And that's why whenever we have a sample size of greater than 30, we say it is statistically significant because we can do significance testing, and there's a probability density function associated with this distribution. Hope I was able to make clear my thoughts and the significance of the sample size. Let's look at future videos to understand the standardized normal distribution, Z statistics, and significance testing in little more detail. Thank you.